All right, we're going to continue on in Unit 2, and this is our last lecture of Unit 2. We've been talking about covalent bonds, and remember, covalent bonds are the sharing of electrons between non-metals to achieve an octet, unless you're hydrogen and you are a minimalist and you just get 2 electrons. So we've talked about the sharing of electrons. Now we're going to talk about specifically how they're shared in a covalent bond. I talked about, what makes it a covalent bond, but now, well, how is that electron density distributed? So when a covalent bond is established between hydrogen and chlorine, you get an electron dot structure that looks like this. I'm going to draw a line for the bond. Now, if you imagine that this bond is a rope and the 2 atoms, hydrogen and chlorine, are tugging on it. If the atoms are of equal strength, the electrons are shared equally. However, let's say you have olive oil and Popeye on opposite ends. And of course, this is right after Popeye has eaten his spinach, right? So if Popeye and olive oil are in a tug of war and Popeye's very strong, Popeye's going to win, right? He's going to pull olive oil over. And so you will see this with covalent bonds. You'll see kind of a tug of war between the atoms. And the one atom that's stronger, or more like Popeye, more able to pull electrons to itself, that's the term that we use in chemistry is electronegative. So for hydrochloric acid, this is hydrochloric acid, it turns out the more electronegative atom is chlorine. So this is like Popeye. And over here we have hydrogen, which is less electronegative. I'm just going to put E in, and that's like olive oil. So when you have an electronegative atom, that means they hog all the electron density. And so chlorine is pulling all the electron density away from hydrogen in this bond right here. As a result, because chlorine is stronger and more like Popeye, more electronegative, pulls this electron density towards itself, chlorine develops a partial negative charge. This is for partial. So it's not a full charge like you see with ionic compounds, but it's a partial charge. And because all the electron density is being removed from a hydrogen, it's kind of like a metal losing an electron. Now this has a partial positive. So hydrochloric acid is an example of a polar covalent bond because this electron density is unequally distributed. So it's polar because you have a partial charge on each atom. A nonpolar one would be where you don't have any electronegativity difference and there's no net movement with this tug of war. It's just static, not moving. So let's define a few terms. I've been talking a lot about electronegativity, but I haven't defined the term. Let's define this. Electronegativity is the ability of an atom to pull electrons to itself. Okay? So chlorine is an example of a more electronegative atom. A polar covalent bond is when you have an electronegativity difference between 2 atoms. So you have an electronegativity difference between 2 atoms of 0.5 to 2.0. So on your periodic table, there are electronegativities listed. I'm going to show you the periodic table that you use, the one that you get in the testing center. On the flip side of this periodic table, you will see, it looks crazy, right? This does not look like the periodic table one. If you're having this reaction, that's good. That means you're becoming more and more familiar with the periodic table. I always caution students, if something's not going right, if you can't find what you're looking for, more than likely you're looking at the wrong side of the periodic table. So for 95% of our work in this course, we will use this side of the periodic table. When we're talking about electronegativity, we will use the other side of the periodic table. And there's a key at the bottom of this periodic table. And there are two columns of numbers. The column on your right, the top most value is electronegativity. So there's also a table of electronegativity. It's a pretty simple table in your textbook. Figure 4.5. These are the key atoms that we would be looking up electronegativities for. So it's kind of nice to have this simpler version compared to this, oh my gosh, what am I getting myself into? You can establish whether a bond is polar covalent or nonpolar covalent by looking at the electronegativities on these tables and subtracting them. So I want you to look up the values for the electronegativities of these atoms: carbon, nitrogen, carbon, oxygen, chlorine, chlorine. Hit pause, look that up either in your book or on your periodic table, and then come back to this. Okay, so now what we found, the electronegativity for carbon is 2.5, and I'm just going with the book values. Your periodic table has 2.55, but we're just trying to get an idea of whether these are polar covalent or non-polar covalent. So whether you take 2.55 or 2.5 does not matter. Nitrogen's 3.0, carbon 2.5, oxygen 3.5, chlorine 3.0, chlorine 3.0. So if I subtract these electronegativity values, so electronegativity difference, so I'm going to take 3.0 minus 2.5, I get 0.5. If I take 3.5 minus 2.5, I get 1.0. If I take 3.0 minus 3.0, I get 0. So I can classify these bonds now that I have the electronegativity differences, and the first two are polar covalent bonds. So both of these are polar covalent bonds. And I wouldn't have known that if I hadn't looked up the electronegativities on the table. Now, chlorine and chlorine, this is an example of a nonpolar covalent bond. Okay. Now, we're going to kind of apply polar covalent bonds to molecular shapes, and another property of molecules called polarity. So moving on to page 15, I have the question, how can you tell if a molecule is polar or nonpolar? So I want to point out here, I'm not saying a bond. This is not a bond. This is a molecule. So an example of a molecule would be water, ammonia, methane. These are all examples of molecules. I want to know whether they're polar or nonpolar. And you think, why is she asking me this? I don't get chemistry. What? The reason that it's useful to determine if a molecule is polar or nonpolar is because polar will mix with water. Nonpolar not mix with water. So it's kind of something that we might take for granted now. You know, you've kind of experienced a lot of different things, I'm sure, in terms of solubility, that they're more like practical applications of this. Most of you probably know that oil and water don't mix. You are very familiar with, you know, like ethanol, alcohol mixing with water. That's because ethanol is polar. So, you know, these are things that you kind of know, but it's just you don't have these concepts associated with them, polar and nonpolar. I'll tell you a little story, so to make this lecture more interesting, so it's not so just all chemistry driven. One time I was getting gas, you know, like we all do. I had a just unleaded gasoline. I did nothing, not a diesel or anything. So my husband was with me. He was pumping the gas, and then, you know, we started the car, and it stalled out, and it was an automatic. So at the time, it was very strange, like, and it was a new car, like maybe, you know, 6 months old. So it was strange. Like, why in the world is this stalling out? And so we tried to start again. It stalled out. Then, fortunately, we'd gotten this gas very close to our home, so it was kind of getting into the evening. You know, we had no urgent things the next morning, I think. So, you know, we just thought, well, we're not going to call a tow truck tonight. We'll call one tomorrow night. It was a safe area. So we walked home, pushed the car into a parking spot. And then the next morning, a tow truck met us there. And the tow truck driver tried to jump it. You know, they thought, oh, it's the battery. It's got to be the battery. That's so weird. We were just driving it. No, he couldn't start it. So then I towed it to a dealership, and I was working at a radiopharmaceutical company at the time. And so I'd gone to work, and the dealership calls me. They say, ma'am, your car doesn't run on water. I said, excuse me? Yes, your gas tank is completely full of water. I said, really? That's so weird. I just gotten gas. He said, well, you might want to call that gas station because you didn't get gas. You got water. And, you know, and it was just like, I was totally taken aback because it was like, your car does not run on water. I know that. Anyways, so I call the gas station, and the gas station says, what? We haven't heard anything of this. You know. I said, there's only one way that I could have gotten water into my gas tank because we just pumped gas. And then they said, well, you know, oh, and by the way, the dealership said it's going to be about $300 to $400 to get it fixed because my gas lines need to be cleaned out and all that. Fuel lines, yuck. Anyways, so the gas station was not very willing to pay that bill, even though they were at fault. And, you know, and then I said, what about this, you know, $30 or $40 that I spent on gas? And they said, oh, well, we might be able to credit that to your account, but it's going to take a while. I said, you know, we're just not really sure if this is, you know, our fault. And so I immediately get off the phone with them and call the dealership. And I said, can you please save me a sample of this gasoline that was in my gas tank? And so they save a sample. And so I go to pick up the car in the afternoon. And the sample was put in like a Dasani water bottle. And it was so remarkable how much water there was. It was a 16-ounce bottle of Dasani water, and so inside this bottle was muddy water, and then at the top, very close to where the lid is, was like a clear yellow substance, and that was the gasoline. And so, you know, it struck me as like so funny because of course water and gasoline wouldn't mix because water is polar and gasoline is nonpolar. So it was such a nice way to illustrate to this gas station that, yes, this is all water. This is what they got out of my gas tank. So on my drive home, I stopped by that gas station and I said, here is what they pulled out of my gas tank. And there's no way that I'm paying for this gas. And here's the bill. And they ended up paying for it, and they were reasonable. It turns out they had several other cars who had gotten water in their gas tanks. It had rained the night before that I'd gotten gas, and their tanks had filled up with water for some reason. Sounds kind of scary. Why is water getting into their gas tanks? But on the pumps, supposedly that there's a filter that detects water on the gas pumps, and anytime it detects water, then it will shut off automatically, and these filters were not working properly. So at any rate, I learned a nice example of polar and nonpolar, and I never got gas there again, especially after it rained. But, that's a nice example. So there is a good reason why we want to know whether molecules are polar or nonpolar. The way you go about telling whether a molecule is polar or nonpolar, it's a few steps. You're going to have to draw the Lewis structure. Look for polar bonds around central atom, and then finally look at the molecular shape. And what you're looking for is symmetry. Now, a good way to tell if something's polar or nonpolar, if you don't know what it is, you can always try to mix it with water. It's kind of a neat way to do that. But if it mixes, then it would be polar. If it doesn't mix, then it would be nonpolar. So HCl, that's the example that we were looking at on the page 14. HCl is polar. When you place it in an electric field, the HCl molecules orient themselves in a certain fashion. So remember, HCl looks like this. You have the partial negative here, partial positive here. So when you have an electric field, the partial positive is attracted to the negative, and the partial negative is attracted to the positive. So HCl is going to line itself up this way. You have the negative, partial positive. So this is another test, to figure out if something's polar or nonpolar, is to place it in an electric field and see how it behaves. So there is a theory, valence shell electron pair repulsion theory. This helps predict whether molecules will be polar or nonpolar. We'll talk about that. How do you predict if a molecule will be polar? There's an electronegativity. There's a difference of electronegativity of the atoms and the bonds. So you have polar bonds. That's one thing that you need to check off. The other thing is the molecule is not symmetrical. Look at the shape. So I have a table, and I have taken this from your textbook. This is on table 4.6. So the key is looking at the central atom, looking at how many bonded atoms you have, so bonded pairs, number of lone pairs, number of sets, what the shape is. We'll go over this. So I'm just going to copy this down. I have a lot of it filled out. Look at the table 4.6 for what the shape is. When you have two bonded atoms or bonded pairs, I'll put that, I've been using that earlier, and zero lone pairs, the molecular shape is linear. This is like what we saw with HCl. Sorry, not HCl. You see this. I'm just going to do what they have on the table. So it's just linear. If you have 3 bonded pairs, 0 lone pairs, then you have a triangular shape, BF3. Your table does a much better job of what I'm doing. To show you the shapes. If you have 4 bonded pairs, 0 lone pairs, this is like what we saw with CH4. It's tetrahedral. So it looks kind of like this. It is hard to show how the models look in 2 dimensions. It's really nice to be able to use a model kit and show the 3 dimensions. If you have 3 bonded pairs and 1 lone pair, then you have a pyramidal shape. That would be like NH3. If you have 2 bonded pairs, 2 lone pairs, this is bent. So this is like water. And then 2 bonded pairs, 1 lone pair. This is bent as well. So SO2. Okay, so you're probably thinking, well, how am I going to apply this? I don't know what she's talking about. Let's go through these on page 16. Polar or nonpolar? So first things first, draw your Lewis structure. You have 3 valence electrons from boron. You have 3 chlorine atoms, 7 valence electrons. You have 21 plus 3, 24 electrons. So your Lewis structure will look like this. Two, 4, 6, 8, 10, 12, 14, 16, 18, 22, 4. So another way to represent this. Boron's one of those atoms that does not require an octet. Just happy with 6. Okay, so is there an electronegativity difference in this bond? Do we have polar bonds? We have the same bond all around. So let's look at that table of electronegativities. Boron is 2.0 and chlorine is 3.0. So the difference is 1.0. So yes, we have polar bonds. For BCl3, the molecular shape, we're going to have 3 bonded atoms and 0 lone pairs. So that's going to be 3, 0 trigonal, or triangular, sorry. Is it symmetrical? So what that is asking is, are these ropes canceling each other out? Think about vectors. And in this case, since they're all the same bonds and they're pulling the same, it is symmetrical. So because it's symmetrical, this is non-polar. Okay. We'll do the same for water. Water's electron dot structure looks like this. You do have polar bonds. Let's verify this. 3.5 to 2.1. So we have a difference of 1.4. So definitely have polar bonds here. The molecular shape is 2 bonded pairs, 2 lone pairs, so it's bent. And it's not symmetrical. So because of these electrons pushing down, and it's actually more like this, they're both pushing the hydrogens down. You don't have the same angle, so it's not like at a direct tug of war. So it's not symmetrical. So because of that, it is polar. Okay, so I gave you a table to kind of simplify things, because you might think, I don't know how I'm ever going to do this. The following molecular, I'll put shapes. Shapes will always give rise to nonpolar molecules when all of the substituents around the central atom, A, are the same. So molecular shape, you have, this is what we saw with BCl3. And your book calls it triangular. So anytime you have, these all the same, this is going to result in the molecules being nonpolar. Okay, so I want you to work on whether compounds 1 through 5 are polar or nonpolar. This can take a little time. You're going to have to first draw the Lewis structure. And it's okay if it takes time. It's good practice. So I want you to hit pause, and I want you to draw the Lewis structures for all of these, and then go through the checklist. Do you have polar bonds? Is it symmetrical? If it's yes and no, then it will be polar. If it's yes and yes, you get polar bonds, but then it's symmetrical, then it's going to be nonpolar. So try working through these, and if you're not even sure on how to draw the Lewis structures, just count up the valence electrons. That's a start. Take baby steps with this. Okay, so I've gone ahead and drawn the Lewis structures for these molecules. So I'm going to go over each one and tell you whether it's polar or nonpolar. So the first question for NF3, you have polar bonds. Yes. Bonds. This is pyramidal because it has 3 bonding pairs or bonded atoms, 1 lone pair. So that's pyramidal. That's not one of your symmetrical ones on the table above, so it's not symmetrical. So because it's so non-symmetrical, that makes this one polar. All right, let's do the same thing for CF4. Yes, we have polar bonds. The shape is tetrahedral because you have 4 bonded pairs, 0 lone pairs. Because of this shape, and because everything's the same, it's this case here. So CF4 is nonpolar. Okay, water, you have yes to polar bonds, and the shape is bent, 2 bonding pairs, 2 lone pairs, so that's non-symmetrical, so this is polar. Now HCl, yes, you have polar bonds. And you might think, what is the geometry? Well, look at it. It's linear, right? But it's not the same on each side. So it's non-symmetrical, which makes it polar. And lastly, we have BH3. Yes, it has polar bonds, and it's triangular, which is 3 bonded pairs, 0 lone pairs. So it's symmetrical, which makes it non-polar. So that's like the table up here, triangular. So that concludes Unit 2, and I highly recommend that you study. Go over the exam review, which is in the online notes section. It will be helpful. Practice those homework problems over and over again, and will help you tremendously. And I'll see you next time for Unit 3.